So if we now return to what it is we're actually interested in, we just looked at this kind of some of the theory of light and what it does, and how it behaves coming from the sun to us. We're getting an image from our sensor, whether it's an aerial photograph, which is what it is in this case, or to our satellite. And what we get is some colours. But I mean, we're not really interested in the colours, certainly not in terms of remote sensing and GIS. I mean, we might be interested in the colours if we're an artist, but let's just for a moment say that that's not what we're interested in. What we're interested in is what's actually there. We want to translate the colours into things, things that we're actually interested in mapping. So how do we do this? Well, we can look at the colours. That's what we have. Image analysis like this, to begin with, we'll just focus on what colours are in the image. There are increasingly more advanced methods where we don't just look at the colour in a particular place, but we look at the colours around as well. We look at the relationships between the different colours in different places. So we look for objects in the image, how to define those, to try and decide what they are. But the basics of all of this is, what is this colour here? What is that colour, and what might it be produced by? What does that mean? Well, this takes us on to the concept of the spectral signature. So here we have an image that illustrates a collection of spectral signatures where we have the reflectance of light by different types of surface. So here we have a logarithmic scale on the left here, and this is the percentage of reflectance. So it's weakly reflecting here, strongly reflecting up here. And these lines represent different land cover types or surfaces on the Earth. So we have water down here, and water tends to be dark in an image. Where slightly turbid water, where we have lots of movement in the water, perhaps some particles floating around in it, but waves and stuff, will be slightly lighter. We can see some light. Water's a tricky one because and specific angles, look angles, the geometry between the sun and your camera, it can suddenly become very bright. It can reflect the light strongly. But if we exclude that one particular angle, what we're talking about is water being dark, generally speaking. Soils also tend to be quite dark. We can see they're weakly reflecting down here. It increases as we go towards these longer wavelengths, in towards the near infrared here. And then move on to snow and ice and clouds. These reflect quite strongly, very strongly in some cases. They're white in colour, so they reflect reasonably broadly, and they tend to be bright. And then we have this interesting line. This is vegetation. Two different types of vegetation, but let's just generally consider this as vegetation. And we can see that we get this peak here, and then it goes down again, and then it rises again there. This is an important one. This is the visible spectrum here. We go off into the near infrared over there, and we can see that this peak here is equivalent to green light. You may have thought that this was the green bit over here, but it isn't. What we have is the blue, the green, the red, and the near infrared. So vegetation is green. That explains, we don't see this bit over here. What we see is everything here. And as we can see, we've got a peak in the green. That makes sense. Leaves are green, generally. Almost all leaves are green, unless they're dead and they go brown. And some leaves in lower vegetation within jungle environments and other deep forests might be red for particular reasons. But generally speaking, leaves are green. That we can see here. That's good. Let's return back to our camera sensors now, our cameras and sensors, the things observing. We have spoken previously about the signal, the spectral signature, rather, that light is reflected at different intensities and in different wavelengths, which means that our cameras, our sensors, are going to need to sense light at different frequencies. And they also tend not to be restricted to red, green, and blue light. but in a lot of cases we'll actually pick up some near infrared as well. We saw in a previous image that vegetation tends to reflect quite strongly in the near infrared. Satellites will in fact commonly have several bands of infrared data. What does a band mean? It's a section of the spectrum. We'll illustrate this a little more carefully soon. So we have blue, green, red, near infrared, and then various degrees of nearness and mid-infrared light that we can observe. The higher frequency, the shorter wavelength light, we tend not to observe. One, we have this problem with absorption, but even closer to the visible, when we get to ultraviolet and even the violet and the blue light, tends to be scattered more by the atmosphere, which means that the image becomes blurry. We're not sure where the light is coming from. So generally speaking, we're not going to see terribly many bands of data towards the blue end, towards the higher frequency light. We have recently seen a development where some of the higher frequency light is gathered in order to measure exactly this scattering, so that we can compensate for that effect on all the other bands as well, because they will be scattered to some small degree. But when we gather this light, we then need to store it somewhere, and it's stored, as I said, in bands of data, which is grayscale images. So we have a grayscale image of the red light. So going from 0, which is no red light, or at least so little that our sensor couldn't sense it, up to a maximum, in this case, in this illustration, of 255. This is a standard 8-bit data registry. So we have the maximum strength, whatever that maximum is 255. So this is maximally red for our sensor. So let's combine this idea of, let's try and get bands and into this, create a better view of what a band might actually be. And to do this, we'll also bring in something called the spectral signal. So we looked at the spectral signature before. What does the object on the ground actually do to the light? It reflects it back at different levels. So the reflectance, we recognize this part of the image. We looked at this bit before, but as we can see, if we extend the signature out to the farther reaches of infrared, not only does it go up there, but it carries on reflecting quite strongly and then dips down and increases and dips down. So we're getting this spectral signature for the reflected light, the sunlight that's being reflected by green vegetation. Here we have the water and soil signals as well. Down here we can see the frequencies. So this is shortwave infrared here, and then the limitations and the colors that I can actually illustrate this with mean that I've split this up into two different sort of zones, as it were. And here we have the visible and near infrared. So we start off with a high energy, high frequency, short wavelength light here out past the blue, then going through our blues and greens and reds, and then we end up in the near infrared over here, actually more sort of here, and then I'd have to switch to this other scale again. Right. What are these little blobs here? These are bands of data from specifically here from Sentinel-2. So we have band 1, which is looking this very high frequency light way out beyond beyond the normal blue light. So this is highly scattered. But here we have band 2. In this case, is our blue light, and so our image, our sensor, is capturing this bit of the blue and this bit of the green and this bit of the red. And then when we start getting into these other bands now, where we're capturing light of varying in near infrared light here, we can see that this band here, this is actually band 8, and it's quite broad. There's also this band 8A. This is specific to Sentinel-2. All of these numbers are actually specific to Sentinel-2. So that this is capturing a broad range of frequencies in this area here. It's all near infrared, but it's capturing a broad range of them. So the spectral resolution is lower here than it is here. This is a higher resolution, only capturing a short area of the spectrum, a small area of the spectrum. But to do that, if we look here, this is the pixel size, as it were. In order to capture enough energy, there is capturing it from a larger area, a larger footprint on the ground. So the depth of these is indicative of the size of the pixel, and the length along here is indicative of the pureness of the signal that is being, or the light that is being collected. So if we then add on, for example, for our visible and near infrared bands, so we have the blue, the green and the red here, and the near infrared here. These are the bands, as it were. This is what light can actually be captured from our signature. And we can add on these other bands as well with near infrared data. We can see that this band is going to capture light here. And then these final bands with the 60 meter footprint or pixel size down there. But what we actually end up with is a measurement of, so we go from the spectral signature, but because we can only observe these bands, we end up with a spectral signal that looks something like this. So if we're observing vegetation, we would expect to get a strength of signal like this. Hit there and a hit there. We're not seeing anything in between. These areas in between are invisible to our sensor. So we don't know what's happening here. Anything that might be going on with the signature here is invisible to us. We can only go on the signal that we're receiving. And then we can take that signal, I'm just reducing this now down to the 4 most common bands used, and then we translate that signal. We can see that we get different intensities, light intensities. Here, this is our radiometric intensity here. So that we can see that the red light here, we get up in our grayscale image for the red would end up here, the grayscale image for the blue would end up here, the grayscale for the green would end up here, and the grayscale for the near infrared would end up all the way up here. So this is our spectral signal.